Hi, my name is Will Steffen, and for our project, we addressed the growing issue of space debris around our planet by finding an optimal rocket design for debris collection. Our approach to this issue was to break up the rocket into important components we could choose to design that would successfully and efficiently collect space debris from Earth's orbit. We first did research on similar rockets that had been built before deciding on sizing and staging for our rocket. We then did a detailed nozzle design and selected a fuel type. An engine was then chosen and analysis of the rocket's orbit was done. Next, we found what debris we could encounter while considering economic factors along each step of the way for feasibility.
I'm Charles, and I will be providing some background information for our project. Firstly, I will help create some perspective for our project. In August 2021, the European Space Agency reported that there were approximately 29,210 pieces of debris being tracked. A piece of space debris has the potential to orbit around Earth at about 8 to 10 kilometers per second and cause catastrophic damage. One example occurred in 2006 when the ISS sustained a 7 millimeter fracture when an artificial object less than a thousandth of a millimeter collided with its window. This damage could have led to cabin leakages and potentially affected those on board. Obviously, it would be vastly beneficial to prevent this from happening. Next, I will survey the current space debris cleanup effort. Although space debris cleanup has only recently come to the public eye, the community is slowly realizing the importance of it. A few examples are the Clear Space 1 mission commissioned by the European Space Agency in September 2019, the End-of-Life Astroscale demonstration mission, and finally, the experimental space debris cleanup devices designed by those at the University of Surrey in 2018. These three examples use a mix of small-lift rockets of SpaceX launch vehicles to provide passage into space. This helps to confirm to us that a small-lift rocket would be a good design for our project.
Next, we will talk about the design of our rocket, starting with the requirements. The spacecraft needs to be able to reach altitudes that contain space debris. Since most space debris is located in low Earth orbit, this means that the spacecraft must be able to go anywhere from 200 kilometers to 2,000 kilometers. Due to the amount of debris that needs to be cleaned up, the rocket will have to be used multiple times, or new ones will have to be manufactured quickly and for a low cost. Variable thrust will be needed to reach the target altitude, stop, then deorbit so that more debris isn't left behind by the mission. Finally, the vehicle must be safe and cost efficient so that governments would support the project. Now for fuel selection. Liquid propellant rockets allow for a less complex variable thrust system compared to solid rockets. Using two propellants allows for a higher specific impulse compared to a single propellant, but keeps the system simple by not using too many propellants. Rocket-grade kerosene, RP1, and liquid oxygen will be used as the fuel and oxidizer respectively. They can provide the required thrust while being safer to handle and store than some other options, such as liquid hydrogen, which is unstable at standard temperatures. This combination is also one of the cheaper options available, allowing for the technical requirements to be met at a lower cost.
Sizing and staging. We had two main choices for the size of the rocket, small and medium lift. Medium lift rockets are more efficient, but mass deployment of the space debris cleanup system is not yet feasible, so a small lift rocket similar to the 20-meter tall Electron rocket would be best. Nozzle design. We decided a two-stage rocket would be used for our design, so a bell-shaped nozzle would be optimal for this design due to being able to optimize each stage to an altitude range. Engine design. To maximize efficiency, a single Merlin 1D engine will be used for the first stage and a single Rutherford engine will be used for the second stage. The Merlin is much more efficient but too big to be used for the second stage, while the Rutherford engine is not as efficient for the first stage but a good size for the second stage.
The next part of our analysis focused on the space debris itself. According to the European Space Agency's 2021 Annual Space Environmental Report, over 1,200 tracked objects are currently orbiting between the altitudes of 250 and 1,750 kilometers. Of this, approximately 1,000 have a mass between 100 and 1,000 kilograms. The report then goes on to explain that about 60% of the objects in this mass range require some sort of orbital adjustment to satisfy current space debris mitigation protocols. Because this equates to approximately 600 objects requiring some sort of disposal, more than any other mass category, our design was focused around the disposal of space debris with masses between 100 and 1,000 kilograms.
For the orbital analysis, the highest circular orbit that the space debris recovery probe would potentially need to reach is 2,000 kilometers in altitude. The gravitational and atmospheric losses were estimated to be between 1.3 and 1.8 kilometers per second. The total required change in velocity calculated for the mission is between 10,368 and 10,868 kilometers per second. As we plotted in MATLAB using multi-stage rocket velocity change optimization equation and Hoffman transfer equation, we get to display the figure to find the optimal potential to continue with the mission. The calculation results in a first stage to contribute 39% of the maximum total and second stage to do the rest.